person.
Yeah.
Smart.
Long story. It was he and little Andrew.
So.
There
might be one downstairs, but I really don't
know.
know.
Be in one physics lab group.
Yes. Anybody happen to know where's the closest restroom that's not on the ground?
No, I think it's really bad.
Is there only one upstairs? Seems like there's another one back behind.
It's
There's not on this floor. I know that much.
There's not one on this floor at all?
It's a smart classroom. There's no bathroom on this floor.
So
there's one by the entrance up on the fourth floor, but I think there's also one on the other end of the fourth floor.
That would be awful.
I'm probably just getting
To the left, and then there's one back around.
Wow.
There's an elevator.
But you always
You go back, and then there's a hallway. And there's an elevator, I think.
I made sure like my schedule.
I think that's right.
I was in here for 30 minutes. Nope.
Yeah, I think everybody had a problem with that one because we were all trying to work it out.
And thus. Please be careful. Streets and things around here. There was a physics major. Was it 3 years ago? I think she was in my class and she got hit by a bus, and it took her a year to recover. It was pretty bad.
Was it the cat bus?
Yeah.
How did she die? Did she lose her leg?
Pardon?
Did she lose her leg?
No. It was badly injured, but she didn't lose it.
No, there was a girl who lost her leg a couple years ago from the cat bus.
How do you?
My brother knew.
How do you get hit by a cat?
She was close to Bowman Field, crossing the street, that road that goes straight up to Tillman Hall. She was just crossing. I don't know. Maybe she wasn't paying attention. I don't know exactly what happened.
It's always somebody not paying attention.
And there was another girl, physics major, who was killed on campus, bleeding. In fact, I think it was the day she graduated. It was the day or the next day.
And she got hit by
Samantha Cawthorn.
Done.
She hit her head. It was down by the Botanical Gardens. Hit her head. She tripped. I don't know exactly what happened, but from what I understand, she fell and hit her head against something. So, be careful.
Proud of you, Chris.
This is for keeps. You know, there's no do-overs in this kind of stuff, right? There's no extra logs or anything. Okay, so we'll zip right through that until Mr. Hotchkiss gets back, and then we'll end class. We'll say, okay, we're done. And there was a student who every day she would start class, raise her hand. Can we go outside?
That would be quite amazing.
Every day.
Or at least on the roof. That would be different.
And so one day she didn't come to class, and another student raised his hand and said, "Can we go outside today?" So I said, "Yeah, that sounds like a good idea, actually." So we waited until the end of class. I said, "We'll stop 10 minutes early." So we went out to the amphitheater out here, and I said, "Anybody got camera, cell phone? Take some pictures." So the next day, don't tell her. The next day, I put the pictures on PowerPoint. I don't usually use PowerPoint, but I had PowerPoint that day, and I folded in the pictures with the PowerPoint. She was so mad. She was really mad. and I could blame it on the student, you see, because it was his idea. Although he kept saying, he said, I don't think this is such a good idea. She's going to be mad. Okay. All right. So yeah, see, class is over. We finished. Yeah. There was so much. It was condensed into 3 minutes. You know, sometimes you don't need more.
We went outside.
Okay, so let's see. Today is the last day on Chapter 2. We begin Chapter 3 next. So let's go over the homework for today and any other questions you have about Chapter 2. Lengthy, right? There's a lot of stuff in Chapter 2. Notice that we did not do integrals, except we read through it. And that will occur in Chapter 3. He'll actually use integration, or he'll talk about using integration, not actually do it, but he'll talk about it. Don't worry about it. When you're reading through Chapter 3, the integration is a means by which you can undo a derivative, kind of an antiderivative. So don't worry about that when you're reading it. Integration really doesn't come into play very significantly in this course until the beginning of next term. So in January, we'll be doing integrals, a lot of integrals in January. So this first term, we'll just concentrate on derivatives. So there's a sheet with the derivatives you should memorize. It's on Blackboard. Everybody downloaded that sheet. Some of them you have derived yourself. Others you don't. You'll just have to memorize, like the derivative of cosine with respect to the angle and so forth. Okay, so with regards to number 64, finding the tangent to the curve. You could have any function, f of x. So I'll draw some function f of x like this. I'll call it y of x. Any function y of x like this. And at some point, say here, x, you want to construct a vector, a unit vector, which is tangent to the curve at that point. So it needs two things, one direction and magnitude. The magnitude is 1, unit vector. The other would be then a vector, so it has to have a direction, and the direction will be such that it will be tangent to the curve at that point. So the hint that I gave in class was that you could do this if you take 2 points, say x and then x plus delta x, reminiscent to the derivative, and then draw the function at those two values, y of x and y of x plus delta x. And those 2 points can be used to draw a line. So let me draw that in green. I'll draw a line through those 2 points. So, more or less, yeah, I can undo and try it again. I can do a do-over on this, can't I? Yeah, let's do that. So that's better. Okay, so I could draw a line that connects those two. How about a vector that goes from point A to point B? So notice the coordinates of point A. Point A. What are the coordinates? X and y. Y of x. And point B. What are the coordinates? X plus delta x, and then y plus delta y. Where delta y, of course, is y of x plus delta x minus y of x. So how do we draw a vector? Let's find a vector that connects those 2 points. So let's call it T, capital T. What vector would do that? And I can express it easily in terms of Cartesian components. So I want an x hat component and a y hat component. If I have a vector that goes from here to here, what's its x component? Let me draw that vector again here.
Delta x minus x.
Say it again, please, just a little bit louder.
X plus delta x minus x.
Right, yeah. So I have, so here is my vector right here, T. That vector. It's going to be in the x hat direction, delta x. And how about in the y hat direction? delta y, right? Where delta y is y of x plus delta x. Depends on the function. How the rise depends on the function. Different functions will have different slopes, different steepness. Okay, so that is a vector. Now, if we make delta x smaller and smaller, that vector gets shorter and shorter. How about if we were to construct a unit vector from that vector? How do we construct a unit vector? Given the vector, how do we construct a unit vector?
You take the component and then divide it by the magnitude.
Divided by the magnitude. So what's the magnitude of t?
Square root of delta x plus delta y.
Squares, don't forget the squares, delta x squared plus delta y squared. So a unit vector which has that direction. So this is almost right, except it's for finite delta x, right? Almost right, but not quite, because we need to take the limit as delta x goes small. Okay, so that's not quite right, because we still have it in the form of delta x and delta y. So one way is to divide the top and bottom by delta x. That'll do it. Instead, let me go back to the original vector t. Let me divide t by delta x. Call it s. So I'm going to divide out from t. I'm going to divide out delta x. Now that it has a different magnitude than the t vector, but it has the same direction, right? We're just dividing it by a number, so it has the same direction. So now we have another vector. Make a unit vector out of s. It's got to be actually the same unit vector. It's still going to be t hat, because it's got the same direction, got unit length. So we divide by the magnitude. So s hat is s over the magnitude. So it's going to be x hat plus y hat delta y over delta x divided by the magnitude, which is 1, plus delta y over delta x squared to the 1/2. That's really the same thing that we had before. That's the same thing as t hat. It's just that I've divided the numerator and the denominator by delta x. It's only one unit vector that points in any given direction. Okay, so now do you see what the next step is? That's for finite delta x. So that's not tangent to the curve, but we could make it closer and closer to the tangent. Now.
Limit is delta x equals 0.
Yes, sir. So if we take the limit of this as delta x approaches 0 of this t hat. So in every place here, what do we have? We have the ratio of delta y over delta x. What does that become? What's the limit of delta y over delta x as delta x goes to 0?
dy dt.
Yes, it's the derivative, isn't it? It's what we call dy by dx. And it occurs in two places. Or in other words, y prime. I could write y prime there. So I think x hat plus y hat times y prime of x divided by the square root of 1 plus y prime of x squared, and then square root. The square root in the bottom there, remember, is to make it have unit magnitude. Now that's for any function, and then you were given a particular function, x squared, I think. So you could substitute for y prime as 2x. So notice that the tangent depends on x. That vector depends on x. Let's try some special cases. Special case. What if x equals to 0? Let's special case first. Let's special case. Y of x is 2x. I'm sorry, x squared. Then the tangent vector is Okay, now different points. Try some points. Let's try x equals 0. That's at the bottom of the parabola. So what should the tangent curve be? The tangent vector be? At the bottom of the parabola there. So I should draw the function y of x squared like this. There we go. So what should the tangent vector be at the bottom of that parabola? It's the unit vector. Which way should it be pointing? Its tangent should be horizontal. And what unit vector is in that direction?
X hat.
X hat. X hat. It's that way, right? Or the tangent vector should be, the unit vector should just be x hat right there. So let's try it. Let's go back up to the function here. I need to keep pointing here if possible. I need to learn how to do that because it doesn't show up very well if I'm pointing on the screen. It doesn't show up on the recording. So let's see. Is there some way I can point here? Let's see. Sort of. Okay, so that's the example curve we have. Let's try values of x equals to 0 there. And we put x equals to 0, the tangent curve is in fact just x hat, right? The y hat component goes to 0, and then the denominator goes to 0. So in that case, in fact, we do get. That's good. Agrees with what we think it should be. Let's pick some other point. Let's pick x equals 1. Okay, in that case, the tangent vector is going to be x hat plus 2y hat, and then normalized, it would be square root of 5. 1 over root 5, 2 over root 5. I think somebody got that one. Not realizing that they were picking a tangent vector at one particular point. Okay, so that would be, somewhere here, unit vector tangent to the value of x equals to 1. How about x gets really big? So on this curve, we go, whoa. No. On this curve, we go, wow, that's not what I want to do. I've got to find a better way to point. On this curve, we go way out to the right. How's the tangent vector going to be pointing?
Up.
Yeah, up. It's getting closer and closer to up. The unit vector will become almost vertical. So you can see that if we look at our expression for t. So x is large, large and positive. Okay, so now in that expression where x is large, the x hat will be to x hat. We add y hat times some really big number. So that the y hat part is really big compared to the x hat part. And the denominator is getting really big. In fact, the 4x squared is much bigger than 1, so it's pretty close to the square root of 4x squared, which is 2x. So it's pretty close to 2x over 2x in the y hat direction. It gets pretty close to just y hat. So it gets closer and closer to pointing straight up as it gets farther along the parabola, farther out. That's actually a characteristic of the parabola. In the parabola, the legs, as they go farther out, get closer and closer to parallel. A hyperbola, they get closer and closer to perpendicular. So that's how those two are different from each other. Okay, any questions about that? It's an exercise in constructing a vector from some known characteristics and a unit vector given a vector, and playing with derivatives to recognize how the derivative comes out. Puzzled? Okay. Semi-puzzled? Just quiet today. Okay. Okay, number 70. Now again, relating to derivatives, we've got a volume of a sphere of radius r is given by that. Now let's increase r by just a little amount, where delta r is much, much less than r. Or in other words, delta r over r is much, much less than 1, that ratio. The amount of increase of the radius is a small fraction of the radius. Okay, so the new volume is just to take 4/3 pi r plus delta r cubed. Right? We could factor out an r cubed from this. You see what I did? I factored out an r from this, and it's cubed, so I have an r cubed, and then I have 1 plus the ratio. And now you can see why I wrote delta r over r is much less than 1. This is 1 plus something really small. So the new volume is just a little bit bigger than the old volume. So let's look at that. Let's look at this thing. 1 plus delta r over r cubed. Now let's expand that in the binomial expansion. Remember the binomial expansion for cube?
1 cube plus...
Yeah, 1 cubed, which is 1.
Plus 3
times 1 squared, which is 1.
r delta r over r.
Right?
Plus 3
times 1, which is 1.
delta r over r squared.
Good.
Plus delta r over r cubed.
Yes. Good. Everybody okay on that? Binomial expansion? If you aren't comfortable with that, review that one. You need to have that handy. Okay. So delta r over r is a small number, much less than 1. How about delta r? So this is much less than 1. So we're adding to 1. We're adding 3 times some really small number. So it's just a little bit more than 1. If delta r over r is a small number, how about delta r over r squared? Even smaller, right? 100th, 0.01 squared is 10 to the minus 4. A thousandth squared is a millionth. So any small number here is going to be even smaller here. How about the cube? It's that much smaller, right? So this is a percent. This is a percent of a percent. This is a percent of a percent of a percent. So really, this term is much bigger than those other terms. Now we don't want to throw this away because that would say there's no change in volume at all. We're looking for the change in volume. So this is primarily what we want to keep. So let's go over that again. Delta r over r is less than 1, so this is small. This is very small, and this is tiny. If delta r over r is less than 1. So we could approximate this by just that first term. We're throwing away terms that are really small. So we're going to approximate it by that because we're looking for an approximation here. So the volume is going to be 4/3 pi r cubed times 1 plus 3 times delta r over r. Approximately. Throwing away the smaller terms. Okay, how about the change in volume? Delta V is the bigger volume, the newer volume, the volume after the expansion minus the old volume. But you can see the V of r plus delta r has the old volume in it, that first term there. All right, so this is 4/3 pi r cubed plus 4 pi r squared delta r. That's what I get. Let me expand this out here. 4/3 pi r cubed plus 4 pi r squared delta r. Right, expanding that out. And then I'm going to subtract off the old volume, which is going to cancel the old volume. So the delta V, the increase in volume, looks like that. Does that make any sense to you? What does this look like? The change in volume looks like something really vaguely familiar here. How about the 4 pi r squared? What is that?
Derivative.
Yeah, that's a derivative, yes. But I mean in terms of the sphere.
Surface area.
It's the surface area of the sphere. And delta r is the increase in volume. So in other words, if we have a sphere and we make it a little bit bigger by delta r, then the added volume is going to be the surface area times the thickness of that increase. That's the added volume. Just take the surface area and expand it outward by a little bit. And the product of the surface area with the additional thickness is the new volume. So in other words, this is the surface area times delta r. That makes sense. Okay. Yes, sir?
I'm just looking back at this question. When
Yeah.
you take the r cubed out
Yeah.
from the r plus delta r, how does it become delta r over r? Like, I understand it turns into 1, but the...
Right at that step here.
Yes, sir.
So, right, I can write r plus delta r equals r times 1 plus delta r over r. And now let's cube both sides.
Okay.
Is that okay?
Yeah, I get it now.
Yeah, factor down. Okay, but somebody else said the magic word. It's the derivative. The surface area is the derivative of the volume with respect to radius, right? The derivative with respect to radius of the volume is the surface area. That's interesting. For this shape, certainly it holds. The derivative of 4/3 pi r cubed with respect to r gives 4 pi r squared, which is the surface area. Right? So what if we take the next step? What if we take the derivative of the surface area with respect to radius? What's that going to give? You've got to think about it a little bit. Okay. So there you go. Does that make sense? It is really like a derivative, because this derivative here, and the way we set it up, it's very much like a derivative. We're looking at the biggest piece where delta r is really small compared to r, very much like what we were doing when we were taking a derivative where delta x is very small, making it really small, looking for the first contribution that doesn't vanish.
Was it the circumference?
Yeah, it's not quite, is it? Yeah. Yeah.
It's circumference times 4.
Yeah. It's kind of funny. Okay, but let's see. I mean, we'll come back to these questions about constructing volumes from areas and stuff when we do integrals, because that was the original intent of Archimedes. Actually, Archimedes first investigated integral calculus, not Newton and Leibniz, but Archimedes, and it was kind of forgotten and lost. It was fairly recently that it was some of his manuscripts were uncovered, and it was discovered that Archimedes really had come very close to inventing the integral calculus. When was that? 200 BC, 100 BC, something like that. It was Archimedes. Okay. So we'll come back to these questions about areas and volumes and stuff when we do the integrals next term in January. Okay, so here's related to the general question of the kinematics. Let's suppose I have a position vector which depends on time. And let's suppose that it's just a constant vector. R sub 0, the sub 0 indicates very often a constant. So that subscript often indicates a constant. And the name comes from setting the time equal to 0, right? If that is my position vector, then at time t equals to 0, that is in fact the position at t equals to 0, so that's why we call it r sub 0. It's the initial value of the position. It's also, in this case, so this is a suppose. I'm just playing around with things. Let's suppose r of t is equal to a constant. So what is the velocity? the derivative of r with respect to time. What's it going to be?
0.
Yes, sir. Why?
Because r doesn't change.
Right.
R of 0 doesn't change.
Yeah, it's a constant. It's delta r over time, delta t, but delta r is 0. It's not changing, so it's 0. Derivative of a constant is 0, even if the constant is a vector, right? I haven't written any components here. This is just a vector. Remember, the delta r is going to be r at one time times r at another time, and I'm going to take the difference between the two. Here's my delta r. But in this particular case, these two vectors, r of t and r of t plus delta t, are the same, so delta r is going to be 0 in this case. It doesn't change. So the velocity is 0. How about the acceleration, which is the next derivative, the derivative of the velocity with respect to time? It's also 0. Not doing much interesting. Right? Okay, let's take another case. Let's take another vector, which is r0 plus a constant times time. And again, the name for these constants will become more obvious, why I call it r0 and why I call it v0. So let's look at r of 0. What is r of 0? If this is my function of time, what is my r of 0?
R sub 0.
Yes, sir. Right? What happened to this other term? This term, what happened to that when I set it to 0? T equals to 0. It goes away. Okay, so that's why I call that first constant r sub 0. Let's look at the velocity now. Oops. Let's do it in a black pen here. V, first derivative of r with respect to time. Okay, the derivative of r naught, we just argued, should be 0. The derivative of that first term should give 0. How about the derivative of the second term? It's just a constant times time. Even though the constant is a vector, it's still just a constant times time. So what is changing? God bless. What is changing? Well, the constant's not changing, but the time is changing. So what is delta r? Delta r over a time delta t, delta r will be v naught delta t, right? That's the only part that's changing. And so delta r over t, delta t, is going to be v naught. Just taking the derivative with respect to time. It's v naught. So how does the velocity depend on time? Now, v naught is a constant. It's not depending on time. The velocity is a constant. So this is uniform linear translation. Oops. I can't spell. Linear translation. Let's examine this function back here up at the top, this r of t. Let's look at this. Whoa! Dang. No, not what I want. Here. Let's go look at this. That describes uniform linear translation. Let's look at what that vector looks like. And so we have some r naught, some vector, which is the initial vector. Here's the origin of the coordinate system. And then we have some velocity in some other direction. And we add to that position something proportional to the time, the distance traveled in time t, which is going to be v naught t. So we add these two vectors, and that becomes r. R is then r naught plus something which is proportional to time. That's uniform linear translation. And its derivative is, because t is the only thing that's changing, is just the derivative is just v naught. Everybody okay on that? I see some puzzled looks, and I'm puzzled about why you're puzzled. Is this right? If I didn't write vectors, you should be able to do all of this stuff. So all I'm saying is that these vectors here are constants. Okay, so the velocity is then a constant. How about the acceleration? It's the derivative of the constant with respect to time. What is the acceleration? The velocity is a constant, so the derivative of the velocity, 0. No acceleration. Hence, uniform linear translation, meaning no acceleration. Okay? So I've written two different forms down for you. The first one was the thing isn't moving. The second one is it's moving, but it's moving with a constant velocity, just motoring along. Okay, anybody guess the next one? I'm going to do another suppose now. Third case.
Accelerating.
Yeah, and how am I going to write it down here? So the first one had just R of t is just a constant. The second was a constant plus a constant times time. What's the next step? Yeah, it would be another derivative, or really, and there are no derivatives here, so it's another one.
T squared.
T squared, right. I want another power of time, which is going to give me another derivative. Right. So let's suppose R of t equals R naught plus V naught t plus 1/2 A naught t squared. So now we have a R naught, and we're adding a part V naught t, but then we're also adding another part which is, depending on 1/2 A naught t squared, gets really big. I mean, if t gets big, it gets big fast. So that's R. R is composed of three pieces: the original position, then a displacement due to velocity, and then a displacement due to acceleration, this higher term. That's going to be the acceleration. So let's check. How about we get out here? How about we look at R at time 0? What happens to the other terms? What happens to that term? That t equals to 0?
0.
And what happens to that term?
0.
Right, so still true. At time 0, it's that's what we mean by R0. It's where it is at the beginning. So now let's take the derivative. How do we take the derivative? So the derivative of that first term, derivative of R naught, is what? 0, because?
It's a constant.
Right. How about the next term, the derivative of V naught t with respect to time? V naught, because the derivative of t with respect to t is 1. And how about this next term? What's the derivative of t squared?
2t.
The 2 cancels the 1/2. A naught t. So what's happening to the velocity? Yeah, it keeps changing. It could be increasing. It depends on how A naught and V are related to each other. If the acceleration is opposite to the velocity, it's actually slowing down for a while. Then it'll start speeding up again. Depends on how A naught and V naught are related to each other. If the acceleration is opposite to the initial velocity, then it'll be actually slowing down and then speeding up again. How about now let's do the before we do that, let's go back. Evaluate V at 0. The initial velocity is what? So we set t to 0. V naught. Is that clear? This term involving t, set t to 0, it goes to 0. It doesn't matter what A naught is. All right, how about then the acceleration? Let's calculate the acceleration by taking the derivative of the velocity with respect to time. The derivative of V naught with respect to time is 0 because it's told you it was a constant. And then the derivative of t with respect to t is 1, so this is just A naught. So what does that say about the acceleration? It doesn't change. It's the same from the beginning until whenever you quit, right? The acceleration is the same. So I've given you 3 cases here. There we go. Right, there we go. Okay, 3 cases, and all I did was keep adding powers of t. right? I started with a constant, then I added something linear in time, then I added something quadratic in time. If I add a cubic term, I'm going to have now accelerations changing in time and so forth. So I could keep adding more terms here. But I'm going to stop because this gets us already a lot of what we're going to do in the first couple of chapters, for next couple of chapters, 3 and 4. We'll cover that. But no components, no x hats, no y hats, no z hats. This is all just in terms of vectors. The original position, the original velocity, and then the acceleration. All vectors. And you see how those are independent of each other? R naught, V naught, and A naught can be set independent of each other. They can be arranged to be having no relationship to each other at all. Okay, any questions about that? That's an example of kinematics, and that without use of Cartesian components. But if I had Cartesian components, I could also write this in terms of the Cartesian components. So now the components x, y, and z are functions of time. And if the velocity then is going to involve the derivative x dot, y dot, z dot, the acceleration will be x dot, double dot, y double dot, z double dot. So it's also maybe nice to use Cartesian components, depends on the problem. Why, when I take the derivatives, don't I get derivatives of x hat with respect to time?
X hat doesn't change.
Right. Same for y hat, same for z hat. We have set up this Cartesian coordinate system so it's not changing. That's part of the appeal of the Cartesian coordinate system. It's not changing. Whatever is moving around up here, but our reference coordinate system is fixed. It doesn't change. So all measurements are made with respect to this fixed coordinate system, and that makes it easy, because then the derivatives don't involve the unit vectors. They don't change. So it's just derivatives of the coordinates. That will change when we go to another coordinate system. When we do polar coordinates, the unit vector is going to be following the particle, and it's moving, it's changing, and so we're going to have some more complicated mathematics initially. It may be convenient in the long run to have a coordinate system that's moving, right? But we start off with a fixed coordinate system when we're starting this. So, okay, so you have a couple of problems there that involve given functions. I think for number 73, for example, you were given x of t is v naught t cosine phi, y of t is v naught t sine phi, and z of t is minus 1/2 gt squared. Okay, so what is x dot? Remember, it's the derivative of x with respect to time. And you were told v naught and phi are constants. So what is the derivative with respect to time? What is x dot?
V naught cosine.
Yeah. Just look at the time. Treat everything else as a constant. Just look at the time. That's the only thing that's changing. You're taking the derivative with respect to time. How about the next one? I think I'm going to try calling a few people here. I'm going to let Mr. Creer off the hook today. Mr. Disharoon, we'll start with you. If x dot is that, v naught cos phi, v naught and cos phi, v naught and phi are constants, what is x double dot?
V naught sine.
No, sir. So think about what's changing. These symbols represent something, but you're told that they are not changing in time. And you're taking the derivative with respect to time. So you want to look for something that's changing in time. So what's the derivative with respect to time of something that doesn't change with time? 0. There's no acceleration in the x direction, even though you got this fancy trig function in v naught. It doesn't depend on time. Okay. Mr. Mr. Covington, how about y dot?
V naught sine phi.
Good. Because v naught and phi are constants. How about y double dot, Ms. Shaven?
Sure.
Because v naught and phi are constants, right? So same thing. Okay, Mr. Fanning, how about z dot?
V naught tan.
So look at z of t right above. How does z of t depend on time? G is a constant. So you're looking only at the t squared.
Negative half g. Yeah, gt.
And remember 2. There's a 2. Derivative of t squared gives you a 2t. So this is minus gt. Right. Mr. Kelly, g double dot.
Negative G.
Yep. G does not change in time, so you were told that it doesn't change in time. You're not given the significance of these symbols. I'm just giving you a purely mathematical problem without any physical significance attached to it. These things don't change with respect to the variable that is changing, which is time. And so even though they're in there, you might want to start, well, I can remember the derivative of cosine with respect to phi is negative sine phi, but that phi is not changing, right? So there's no derivative of phi involved. Okay. Okay, any questions about the homework or chapter 2, generally speaking? So there will be a test on material, including the material that from Friday, this coming Friday. The test will go all the way up to that time. So the test is one, I should say 1, 2, and a bit of chapter 3, meaning the reading assignment for Friday.
Wait, the assignment due Friday? Or?
Yes, sir.
Okay.
You're going to be reading chapter 3 for Friday and answering reading questions. Your favorite part of the homework
62 reading
is
questions.
63, maybe, I don't know.
Plus or minus 1 or 2.
There are a few reading questions to answer. So that assignment will be on the test as well. The test will be a week from tomorrow. So what is 1926, right? September 26th, Thursday evening, 7 p.m. I'm sorry to say could not get this room. There's another class in here at that time. So just
At 7 p.m.?
yeah.
What do they do at 7 p.m.?
Yeah, I don't know. It will be instead in 101 Kynard. That's the big lecture hall on the first floor in Kynard. Do you know where 101 is? That's the you walk in the main entrance to the building, and it's that big lecture hall on the first floor. There's a lecture hall on all 4 floors. The ground floor, the first, second, third. It's the first floor. Okay, so yeah. I'm gonna plow on to chapter 3 here. You're putting the notebooks away. We got 3 minutes. Can we go outside? No. We're gonna work some more. All right. So chapter 3. Oh, the test will be an hour long. We have an hour slot from 7 to 8. Study guide from chapter 2 would be a good thing to look at. The summary at the end of chapter 2. He summarizes, except we're not going to really do intervals. Intervals will not be on the test. I'm not going to be concerned with intervals. But I might well give you a list of functions to take derivatives of, for example, the ones that you're supposed to have memorized. That may well be on there. And remember, please, derivative with respect to what? The derivative of cosine of phi with respect to phi is indeed negative sine phi. But the derivative of cosine of phi with respect to t is 0 if phi doesn't depend on time. right? So please keep that in mind. Should I write that one down just to be clear? D cos phi d phi is indeed negative psi sine phi, but d cosine phi with respect to t could be 0 if phi is a constant. Depends on how phi might be changing with time, but if it's a constant, it's going to be 0. So be careful of what you're taking the derivative with respect to. You're changing something, and you want to see how the other thing is changing. That's the point. Okay, chapter 3. We're finally getting to it. Impetus, the cause of locomotion. Why does something move? Because it has impetus. Impetus is an older word that's related to, not related in root, but related in meaning to momentum. Impetus is simply an understanding of why something moves. So, remember on the first day of class, maybe the second day of class, I was asking, what is momentum? Chapter 3 is finally going to give you an answer to that. What is momentum? It starts with impetus. If you push something on ice, okay, clearly pushing has something to do with getting it moving, but then you stop pushing and it still slides. It keeps on going. If you're driving on ice and you lose traction and you get this feeling, it doesn't matter what I do with the steering wheel anymore, I'm just sliding. You're going to keep going that way, that fast, until something happens, right? You're going to run off the road, you're going to hit something, something's going to happen. But until then, you're just going to keep going that fast in that direction. That's impetus. You keep moving because you have impetus. The thing you start sliding on the ice keeps moving. It persists in motion because it has impetus. Now, there's nothing outside of the body that's keeping it moving. And this is the error of Aristotle. Aristotle makes that mistake. He thinks there has to be something to keep the thing moving. There has to be, and he said, suppose maybe it's air. The air keeps coming around behind, it keeps pushing it. The air is what keeps it moving. He wanted to have something outside of the body to keep it moving, which is what we call a force. Right? And that's clearly there is something outside of the body. When you're pushing it to get it moving, clearly that's outside of the body. So it does have something to do with motion, something external to the body. And yet, there is still this thing, external influences put aside, something will keep that thing moving, and that's impetus. So, simply speaking, it's the cause of locomotion. Chapter 4 is going to be about force. So that's the order of topics. Chapter 4 is about force. Force is how impetus is changed. A body may have no impetus, and so it's at rest. And then you push on it, and now you're giving it impetus. And as long as you continue to push on it, it will have more impetus. You stop pushing, and now the impetus is going to persist. As long as you don't act on it again with some other force, that impetus will keep it moving. So impetus has both an intensity and a direction, but impetus is a quality of the body. It's not a quantity, it's a quality, even though it varies in intensity, right? It's what keeps something moving.